Assalamu alaikum.
Walaikum salam, sir.
Walaikum salam.
Okay, so welcome back after the midterm exam. Okay, so today we are going to talk about a very useful tool in microwave engineering known by the name of Smith chart. So as a microwave engineer, you will come with this term very often. So before using this Smith chart for microwave circuits, I want you to understand the background of this chart and why you will prefer to use this Smith chart to solve different problems. So for historical point of view, this chart was developed by a person known by the name of Peter Smith in 1939 at Bell Telephone Laboratories. Okay, so that is why this chart is known by the inventor name, that is Smith. Okay. Now, what is basically Smith chart? So step by step, I can talk about the main features of the Smith chart. So the main, if you describe Smith chart in a very simple term, then you will say that it is just a graphical tool. So what is Smith chart? It is a graphical tool for solving transmission line problems. Now, someone may say that this chart, which was developed way back in 1939, and right now we are in 2021. So, why this chart is still significant, even though we are now routinely using personal computers to solve different engineering problems, as well as now there are a number of CAD tools available. But even then, this chart hasn't lost its significance in modern microwave engineering circuits. So even when you use any modern tool, any 3D simulation software, this chart is also part of that software, as well as different testing equipment that are used for testing microwave circuits. This chart is also included as part of graphical representation. Okay, so it means that this chart is going to be used for foreseeable future. Okay, so let me write it down. So it is an integral part of current CAD software and test equipments for microwave design. And as a microwave engineer, what is the significance of this Smith chart? So a microwave engineer can develop a good understanding about transmission lines and impedance matching problems by learning to think in terms of Smith chart. As I've pointed out over here, that it is a graphical tool. So as a microwave engineer, if you have a good understanding of Smith chart, then you will be visualizing transmission lines and impedance matching problems in terms of Smith chart. Okay, so at the back of your mind, you will be looking at any microwave transmission line or impedance matching problem in a graphical manner by visualizing Smith chart. Okay, so what is basically Smith chart? How it look like? So let me draw a very rough Smith chart, but that will give you a basic understanding, and then we will try to find out how it was developed by Peter Smith way back in 1939. So graphically, if you look at the Smith chart, you will find out that it consists of number of circles. So let me draw the Smith chart. And if you have a book with you in hard form or in soft form, you can also look into the page number 64 of the textbook, and you will be able to see the clear Smith chart. Okay, page 64 of the textbook. Right now I'm drawing the Smith chart. Okay, so Smith chart, uh, it look like this. Okay, so you have one big circle, then you have one horizontal line, which is almost dividing this circle into two parts. That is, this is the upper half portion and this is the lower half portion. And then what is inside this Smith chart? So let me draw some more circles. So if you are looking at the Smith chart in your book, you will find out that there are circles like this. Okay, so you can compare these circles with the original Smith chart in the book. Okay, so these are some of the circles, and then you will also find some lines like this. So this is roughly how Smith chart will look like. Okay. So if someone is looking at this Smith chart for the first time, he will find it quite intimidating because it's very uh, complex type of graph. But at the end of today's lecture, you people will be able to find out what each of this line, each of the red lines and each of the blue lines that I have drawn on this big circle, inside this big circle, how we can also draw them with the help of an equation. So every line that or every circle that I have drawn on this Smith chart, at the back of this line is some kind of an equation that Peter Smith used to arrive at this Smith chart. Okay, so how Smith was able to come up with this chart and why it's so useful for us as a microwave engineer. Okay, so let me uh, try to develop this chart in a manner which in a similar manner that was used by Peter Smith. So step by step, I'm going to explore this Smith chart. So the first thing that you need to understand is that the Smith chart that you are looking at right now is at the back of this Smith chart is basically uh, reflection coefficient. Okay, so what I'm going to talk about is it is based on polar plot of voltage reflection coefficient, that is gamma, which we have already introduced in this course. So Smith chart is based on a polar plot of voltage reflection coefficient. So let me uh, explain this concept. So reflection coefficient, if you remember, is a complex quantity. If I want to represent this complex quantity in a polar form, so I need to have its magnitude, and then I need to have its phase. So there are two things associated with voltage reflection coefficient. One is the magnitude, and the second part is the phase. Now, the magnitude of the reflection coefficient, if you remember, the range of the magnitude of the reflection coefficient is from 0 to 1. This is something that we have covered in our previous lectures. Okay, so what is the range of reflection coefficient magnitude? The minimum value is 1 and the maximum value, sorry, minimum value is 0 and maximum value is 1. Okay, this is something which we know already. Similarly, the phase, you all know that phase can change from 0 to 360 degree, or we can also say that phase can vary from minus 180 degree to plus 180 degree. So this is something which we know about uh, reflection coefficient. So if I want to plot reflection coefficient graphically, so I know that the magnitude of the reflection coefficient is from 0 to 1. So we can represent the magnitude as a kind of a radius from the center of the chart. Okay, so if I have a plane, and if I want to represent the magnitude, so let's consider some examples. So let's say you are given that the magnitude of the reflection coefficient is, let's say, 0.5, and the angle is given to you as 45 degree. So if I want to represent, let me call this plane as gamma plane. Gamma plane. So if I want to plot this example number one, so there is, I need to draw a vector with the magnitude equal to zero 0.5, and I have to draw it at an angle of, so angle is usually measured from this axis. It is measured, it is taken in the counterclockwise direction. So this is 0 degree. So how I will represent this particular example, I will draw a line. So let's say this is 0.5, and then this angle is 45 degree. So this, let's say this is point A. Let me call this as point A. So this is point A. Okay. Similarly, let's consider another example, example number two, and let me call it point B. And now we have magnitude of reflection coefficient equal to, let's say, 1, and phase is equal to 90 degree. So in gamma plane, how I will draw this? So I will draw a line with the magnitude equal to, let's say, this is 1, and this angle is, of course, 90 degree. So this is now point B. And you can keep on taking any value, but the main point that I want to make you understand is the magnitude, because the magnitude, the maximum magnitude is equal to 1. So if I draw a circle such that the radius of that circle is 1, so let me call this as unit circle. So no matter what value of gamma you take, we know that the magnitude cannot be more than 1. So it means all possible values, any value of gamma, it will be inside this circle. It will be inside or on this circle. Okay. So the point is, all possible values of gamma, they will lie within this unit circle in the gamma plane. Okay. All possible values, no matter which value you take, we will be anywhere within this circle. But where we will be within this unit circle, that will depend on the magnitude part, and it will depend upon what is the angle. Okay. So the Smith chart that I had drawn before, you can see this black line that I had drawn before. This is actually the same unit circle. This is the same unit circle. Okay. So what is the main point that you can take from this discussion? All possible values of gamma will lie within the unit circle, within the unit circle. Now, this representation of voltage reflection coefficient in gamma plane, it is not that much useful. Okay. If I am given this information that reflection coefficient is equal to 0.2 e to power j 60 degree, if this information is given to me, I can represent this information in the gamma plane. Okay. But from microwave engineering perspective, this representation of reflection coefficient in gamma plane is not of any use. Okay. So what is the utility of the Smith chart? If the point is, it is based on a polar plot. So what I'm going to draw is this axis is normally not drawn on the Smith chart. So if you look into the book, this axis will not be there, but I just want to show you for your understanding purposes. So you can look at it as if this line, horizontal line, and this, let's assume that there is also some vertical line as well. So this represent, of course, I have represented reflection coefficient in polar form, but you know from your complex number knowledge that any complex number can also be represented as if it has some real part. So let's represent it by gamma r. And it has some imaginary part. So let me represent the imaginary part by gamma I. So this number, which was represented in this form, you can also represent it in this manner. So based on that, this axis will be called as the real gamma axis, and this axis will be called as imaginary gamma axis. And this is what I'm calling as gamma plane. So Smith chart is actually plotted on this gamma plane. Okay, you have this gamma plane, and then on top of that you have this number of circles, and those circles are actually called as Smith chart. But what is the use of these circles, the red circles and blue circles? Of course, right now you may think that these blue lines, why I'm calling them circles, but actually they are part of a circle. Okay, we have taken only a portion of the circle. So at the end of this discussion, you will know why I am calling the blue lines also as circles. Of course, the red lines are circles, which is that there is no confusion about them. You may be confused that why I am also calling the blue lines also as circles. Okay, but it will be clear to you in a short while. Now, what is the advantage of Smith chart? Okay, because just plotting reflection coefficient on gamma plane, it is not that much useful for us. Okay, so what is the main point? So let me write it down and then I will explain it. It can be used, so I'm talking about Smith chart. It can be used to convert from reflection coefficient to normalized impedances, as well as we will also consider admittances as well. It can be used to convert from reflection coefficient to normalize impedances or admittances and vice versa. This is something that I talk about before midterm as well. So let me refresh your memory. If there is a transmission line with characteristic impedance Z0, and if it is connected with some load ZL, and assuming that ZL is not equal to Z0, so any signal coming from the source side, when it arrives at the load point, some part of it will be reflected gamma. And we know that this gamma is equal to ZL minus Z0, ZL plus Z0. So depending upon what value of ZL is given to us, we will use this equation to represent the load in terms of its associated reflection coefficient. So every load, what is the main point? Every load impedance will have its unique reflection coefficient. It's not possible that you have two different loads and they have the same reflection coefficient. What is the main point that I'm talking about? Every different ZL will have a different gamma. So in microwave engineering, I can use impedance to specify my load, or I can also use gamma to represent my load. Okay. So information about load is either in terms of impedance or it is also in terms of gamma. So now we can represent our load in both possible representations. You can use impedance of the load to represent it, or you can use reflection coefficient to represent your load. And if ZL is given to you, you can find out its reflection coefficient. And if reflection coefficient is given to you, you can use this equation to find out what is the corresponding load. But this is, if you use this equation, so we will say that you are using equation, you are using analytical method to find out the value of gamma from ZL or the value of gamma from ZL. But now we can do the same thing with the help of Smith chart. And this is the statement that I'm making. What is the statement that I have written? It can be used to convert from reflection coefficient to normalize impedances. So this conversion, which is represented in a mathematical form, but what Smith chart enable us to do is to perform this transformation graphically. So you will not be using this equation, but you will be using Smith chart to convert the load impedance into its reflection coefficient form, or the reflection coefficient form into the associated impedance form. How it can be done, I will talk about it, but this is the meaning of this statement. But there is another important thing that you can notice over here is that I have used the word of normalized. I have used the word of normalize. So with that, I can make another important point about Smith chart, and that is Smith chart is used for normalized quantities. The normalization constant is usually the characteristic impedance of transmission line. And if you remember, the symbol that we use for characteristic impedance of transmission line is Z naught. So whenever you use Smith chart to solve any problem, the first thing that you need to do is normalize your given quantities. Okay, and of course, by quantity, I means either Z or Y. So just to give you an example, if you are given information that load impedance is ZL, represented by this capital ZL, okay? So this ZL is my load impedance. If I want to represent, or if I want to show this load impedance on Smith chart, if I want to show ZL on Smith chart, the first thing I need to do is to normalize it. And how I will normalize it? I will divide it by Z naught. So what you will do? You will take ZL and you will divide it by Z naught. And this ratio will give you the normalized version. So normally the normalized version are represented with small letter. So I will call it small ZL. Just to make sure that you are not confused that whether I am using the small z or capital Z. For this lecture, I will represent the normalized impedance by dash. So ZL dash. What is ZL dash now? ZL dash is now the normalized load impedance. What is capital L? Capital ZL is your actual load impedance. And when you divide it by Z naught, you will end up with a normalized version of that. So this is another important point about Smith chart. Okay. Now coming to the main point, that is, what are these red and blue lines representing? So before I develop the equation, another important point is if load information is given to you in terms of its impedance. So load information is given in terms of impedance, let's say. So you may be given that Z is the load impedance and it has some real part, let's call it R, and it has some imaginary part, let's call it X. Now, if I want to represent this information on a graph, so this horizontal line will be representing the real part and this vertical line will be representing the imaginary part. Now, for all passive loads, we know that the value of R, it can never be negative. It will always be positive. So the minimum value of R is 0 and the maximum value is infinity, which means that the range of all possible value, whatever is the load impedance, the real part will be somewhere on this line from 0 to infinity. Whereas the imaginary part, which is representing the reactance of our load, because it can be capacitive as well as inductive. For inductive load, it will be positive. For a capacitive load, it will be negative. So this X can be either in this region or it can be in this region. So the point is, all possible values of Z will be within this region, So this is Z plane. So on Z plane, if I want to represent my load graphically, it will be anywhere within this region, depending upon its real part and depending upon its imaginary part. If X is positive, then we know that we will be only within this region. So this is for positive X. Okay, and if X is negative, then we know that this green area, it is representing minus X. Okay, so this is the possible region where any load will lie. So I will say all possible load impedances will lie within this shaded area. And you can see, if I ask you how much is this area, so of course you will say this is the infinite area. Okay, if I consider all possibilities about z, so z can have any value, so it means this whole region. And of course, because this is from 0 to infinity, similarly x is also from minus infinity to plus infinity. So the region that we have to draw to represent all possible value of z, it has infinite area. Okay. Now with this background, let me talk about Smith chart in the next session.